Okay, so someone asked me, can I explain how this thing works? So I figure, all right, well, I'll give this a try here. So we'll start from the bottom up. How's that? Um, and of course, you can play these in any order you want. But this one will be about how this little tube circuit works. Now, I'll put a link in the description that there's a web page, outerworldapps.com/PDP-8V, and I think it's about a third the way down. It has a little schematic of the tube section. So I'll draw it here, and hopefully you'll be able to see it. Yeah, I can draw it nice and big. Resistor, resistor, resistor. Okay, so here is going to be the output from the gate. Okay, and I wanted to keep the logic levels as close to the usual 5 volts and 0 if I can do that, right? That was my initial target, was can I make this run so that all the logic is processed at the usual, these days usual 0 and 5 volts. So I figured, okay, well, I'll have a voltage divider, right? And then my plate of the tube will come off here, right? Plate, grid, cathode, tube. Okay, and I have a high positive voltage up here, and resistor, 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 and a negative voltage down here. And when the tube is off, this node will be some high voltage, right? And when the tube is on, it pulls us to a lower voltage. And if this gets pulled to a lower voltage, this output will get pulled to a lower voltage. So, with the tube not conducting, tube off, right? I want this to be around 5 volts, right? So 5 volts will give me a 1 coming out of here. And then, out here is going to be the diodes and whatever that this tube is driving. So this would be, some pull-up resistor to plus 5 volts. When this is a 1, so I have 5 volts here, 5 volts plus 5 volts here. Some resistor, and then the diodes on the input gate and all that stuff, whatever that is. And that gives me my 5 volts here. I'll draw that bigger, plus 5 volts here. So basically no current is going to flow here when this thing is at 5 volts, okay? So I don't really have to concern myself with the output network at all when I'm trying to figure out, okay, how to make this 5 volts. And the tube also is not conducting. So I'm not concerning myself with the tube either when we're outputting a 1. So really all we have to do is concern ourselves, what are these 3 resistors? So there could be a lot of things really. And I thought, okay, well, typical tube voltages, is around like 100 volts or so. And it came down to what power supplies can I buy, relatively cheaply and all that kind of stuff. And I thought, okay, well, I could, grab two 48 volt supplies and a 24, and that would give me 120 volts. And that sounded like a good tube voltage. Can I design it and make it work with that as a power supply? Because they're pretty cheap and all that stuff. So I started out, okay, well, what if I have 120 volts here? 120 up there. Okay, nice and big numbers, I guess, 120. So you put 120 volts in there. And then I wanted to get this to 5 volts. And so I played around with numbers again. And again, the 48 volt supplies are cheap. Okay. And this would have to be some negative voltage down here, right? How else would you get 120 volts down 5 volts? So I made this 996, minus 96 to start with. All right. So with this circuit, just again, with this is 5 volts, okay, you're not going to get any current going this way. And the tube is not conducting. So what resistances are needed to make this give me 5 volts here, more or less, right? So I played around with some numbers and stuff like that, and I came up with you notice the design, there's the 26.7K here, and coincidentally 26.7K here works, and 46.4, I think I have 46.4K, ohms, of course, ohms, and these numbers worked out. Now you could, of course, use anything in these ratios, and we don't really know, exactly how these are split yet. Okay, but we know, we could do all the algebra and all that stuff, and I'm not going to grind through that. This is just, the general idea of what's happening here. So anyway, yeah, these could be any numbers in these ratios, right? And you want to have minimal current through here because you don't want to be dragging um, a lot of unnecessary current. But you want to have, so a minimal amount of current that will get the job done is basically the way it works, right? Okay. But you have two factors now that will determine what are the absolute values. Because you could say, okay, well, these are really ratios, of what, about 2 to 1 or something like that for these resistors. And like I said, with it open like this, you get 5 volts coming out here with these resistor values. Okay. But now you have the factor of, okay, when you turn the tube on, it's going to conduct and pull this node down. Okay. And it will pull this node from 5 volts down to, hopefully down to 0 volts or less. Okay, if it's, minus 20, hey, that's good. But if it's 0 volts, that's good enough, right? Because you want this output volt here going into the gates, and I'll go over the gates over here at some point. But you want this to be able to pull down the gates um, so that this voltage is 0 under the maximum load. Now, I wanted to be able to pull down 10 gates, drive 10 gates with this. So I used 47 kilo ohm resistors. Again, it was just an initial guess to start with 47 kilo ohms and then see if all the numbers worked out. So if I have 10 of these, this effectively makes this a 4.7K resistor because there's 10 of them in parallel. So if you make that a 4.7K resistor, right, and you have this diode drop across here, so really you have 4.3 volts and a 4.7 kilo ohm resistor. So you're going to have 1 milliamp worst case going in here, right? 1 milliamp going in there. And so that's going to, again, pull up on this a little bit, and you have to have, are the resistors the right value so that if you have a milliamp going in here when this is 0 volts, we don't have 5 volts going in here anymore, we have 0 volts. We're doing the other case now of 0 volts. So with that 4.7 kilo ohms, you have a milliamp going in there. And now these tubes aren't, that great of conductor when they're full on, at least these little, little bitty tubes. So I think I used like 18 or 20K, and this is something I measured experimentally, and it's also on the data sheet as being put ground here because the cathode is, more or less at ground. And so this is like 18K or 20, maybe it was 20K I used. And I think the data sheet shows that it's in the low teens, but if I use these values here, that'll give me a worst case, right? So if you figure out what all of this stuff is, you'll see that, yeah, it's able to pull this down to 0 volts. And again, you can work out the arithmetic for doing that. I'm not going to pound through the arithmetic here. Okay, but there's the idea. When this is open, yeah, I should mention this is about 60 volts, right? You get 60 volts in the case of this being a 1, and it's around 40 volts when the tube is conducting and you get 0 volts on the output. So, and that's not really all that important what these voltages turned out to be. The main thing is, does it conduct enough? Is this tube strong enough at 40 volts to pull this node down so that this goes down to 0 volts, where this output, the loads are trying to pull it up to 5. Okay. So yeah, it works out that this is 0 volts or maybe just a little bit less under this load condition. If you take these output resistors off and the diodes off and all that stuff, disconnect all the next stage gates, this goes down to like -10, -20, something like that. But with it fully loaded with 10 loads, it pulls it up to 0 volts. Okay. So that's basically how the output stage, how these voltage dividers work. It's not all terribly complicated. You just have to pick some values so that these numbers work out and that the tube is able to conduct strong enough to pull it down. And I sort of just experimented with I put a 27k ohm resistor on this plate and measured how much it would pull it down, and yeah, it seemed to match up with the data sheet quite a bit, the 6J6 data sheet. Okay. So now we can talk a little bit about the input circuit here on this grid. I said I was going to do that. So I'm going to redraw it over here a little bit. Here's the plate, right? And then the grid is here, and the cathode. Okay. So now, what do you have to do for a grid to make this work? Now, tubes kind of work like JFETs, right? If you don't connect the grid to anything, they're a diode. They conduct. Okay. Again, not all that great. They don't conduct all that great. There's still a gap of air, or not a gap of air, even a vacuum rather. So there's still, 18 kiloohms or whatever, or 15 kiloohms between this plate and grid when the tube is fully on. Between the plate and the cathode, right? So it's not all that great of a conductor, but it's good enough, right? It's good enough for us to work. Now, if you want to shut the tube off, this grid has to be at a lower voltage than the cathode, okay? So if you grounded the cathode, right, put the cathode at 0 volts, you'd have to make the grid -3 volts, okay? Because it takes, if you look on the data sheet at, plate voltages, these low plate voltages, it only takes -3 volts on the grid to shut the tube off so it doesn't conduct at all, okay? So, but I'd like to use, positive voltages, 0 volts on the grid, 5 volts on the grid, right, to turn it off and on. So I put the cathode at +3 volts. So if you put +3 volts in here, then if the grid is at 0, then the grid is 3 volts below the cathode, and that's enough to shut the tube off. So putting 0 volts in here shuts this tube off and gives you the high voltage here. So you get the +60 coming out of here with, all the resistors connected up. Okay, so 0 volts on here makes it 3 volts lower than the cathode. So the electrons try to boil off the cathode, and they see that grid is all negative, and they say, we're not going anywhere, right? So they just sit there and stew on the cathode as long as that's 0, right? Now, if I want to get a 1 out of this, okay, remember my circuit over here where I put 5 volts into this mess here, and this goes on to the grid, right? So this will drive the grid up to, as long as I get it above 3 volts, if I put 3 volts, a +3 volts in here, right, this will cause the tube, the electrons will get through the grid now because they're at the same voltage as the cathode. So the electrons will just go right through the grid and hit that plate and pull the voltage down to my 40 volts. And so that's how that works. Okay. So it's really basically as simple as that. When I have a +3 volts or more on here, okay, which is, so the 5 volts should easily be able to pull it up to 3, Okay, then it will fully conduct, pull this plate down to 40 volts, and then you get a 0 coming out of here. So 3 volts in ends up being 0 volts coming out. If you put 0 volts in, right, the tube's going to stop conducting. You'll get 60 volts here, and you'll get the 5 volts on the output. So that's how that works. Anyway, so that's basically how the tube part works on here. There's another thing on here called the grid leak. So you put a resistor here, and well, I guess that will be better explained with the diodes. So let's put some diodes and make a gate out of this, and then we'll explain the grid leak. So here we have our tube again, right? Plate, grid, cathode. We're putting 3 volts on here, plus 3 volts on that cathode. Go in there. And now what do we put on this grid to actually make gates out of it? Okay, so the gates are basically and or inverts. Okay, and or invert function. And again, you can look on that web page and it explains all this on the web page. But there's a diode there, and there's one of the 47 kiloohms, and that goes to 5 volts. 47 kiloohms. A diode, and then you put diodes going this way for all your AND terms, right? So here's the inputs here. Now if you want another OR term on this, then you can stick another diode, another resistor here like this, and that gives you another OR term to the AND or invert gate. Plus 5 volts, 47 kiloohms, and a diode going this way, and a diode going this way. So with just these gates here, this would be like this. This would look like, right, there would be my output, and then this is the AND term. So there's a couple of inputs here, and then this bottom one just has one thing like that. So that's this gate here, right? ABC. If you did ABC, that's pretty silly, but it's enough to show the point. And then coming out here, out the plate, this would be out the side of the voltage dividers. So voltage dividers, remember, were here. And here's your output. We'll call this X, your X output, X. Okay, so that's how that goes together. And anyway, you can see that when this input, let's say this one is low. So this one here is at ground or 0 volts somehow, not necessarily wired to ground, but a gate outputting 0 volts, let's say. And so this is going to get pulled down to 0 volts. Well, 0.7, 0.7, let's say plus 0.7 volts. And then you'll have the voltage drop across this diode here. If this diode is at this point here is at 0.7 volts, then this point here is going to be 7 volts, 0.7 volts below that. But it doesn't really have anything to pull this down to 0.7 volts. So that's why you need a little resistor in here. So we put a little resistor in here, the grid leak, and I used 150 kiloohms for this. Okay. If this resistor is too small, then this 47 kiloohm resistor here won't be able to put enough voltage to drive this grid up to 3 volts like we need it. So this resistor here can't be too small. If you made this 47 kiloohms, then you would only get 2 volts here maybe, because you got this diode drop here. So you'd maybe only get 2 volts here, and we don't like 2 volts. We like nice, half a volt or less for a 0, and 3 volts or more for the ones if we can get them. If you get 1.5 volts, then the tube's going to be half on, and you're going to get a half, you're going to in between voltage out here, and we don't want those, because then it's not going to be all that reliable, right? This circuit isn't going to act like, okay, we got a solid 1 here or we got a solid 0 here. So this can't be too small. And if you make it big, then you're going to get timing, because then you have a large this capacitance in here. Those going to look tubes only look like a couple picofarads, but you want to make this as small as you possibly can on the other hand, so that your timing is as good as you can get it. So anyway, that's why I have 150K. I originally thought 120K, but then I kind of chickened out because I want this voltage to be good. Maybe you could experiment with it again, and maybe I could experiment with it again and get 120 kiloohms and convince myself that that would work. But I thought, I'm going to make 80 of these boards, and I better put resistors I know that are going to work. So if you put 120K in here and try it, you might be able to get a little more speed, because then it's going to work this capacitance a little bit better on the tube. But yeah, whether it would be significant or not, it's another guess. But anyway, 150 kiloohms works, so we can use that. And again, it's to when this node goes high, it has a path for the current to flow in there. And when the node goes low, when this gets pulled down to 0 volts, okay, you also want this to, this basically would open up. Okay, this would become an open circuit here. And then you want electrons to charge up through this, because they wouldn't have a path to get through here. But that's how the tube circuit works. So it's pretty simple, and how to make a gate out of it. And that's, I guess, that's pretty much it. Making a flip-flop out of these gates, I already talked about in one of the sequencer board videos. So that's how the flip-flops work. So you have gates here made out of the tubes, and that's how you put these together to make gates. And we showed how to make flip-flops out of a half dozen gates. Take 6 NAND gates to make a flip-flop, and that's about it. Oh, there's one thing here. To get this 3 volts, someone said, you can't use Zehners. They weren't invented till 1955. Well, all right. You could use a separate 3-volt supply in here. I kind of cheated, of course, because I had the 5 volts everywhere, and I put a 3-volt Zehner in here, with the sum resistor. I think I used 220 ohms. Probably could use, it isn't all that important, because I think really, and I should have thought of this before I put the 5 volts in here, but really the current is flowing through here, and I think the Zener gets its voltage current, enough current to pull it up through here, but putting the 5 volts there can't hurt. And there's a capacitor here, of course, so that it stays steady at 3.3. Actually, these are 3.3. I ended up using 3.3 volt Zeners. And, a 0.01. Not all that important. And so that's how I get the 3 volts on that cathode there, is just with a Zener, because I had 5 volts. If you want, you could put a separate supply there and put 3 volts in there. So anyway, I guess that's the complete circuit we've got. And yeah, there's, capacitors on here, of course, for bypass, to the 120 plus 120. There's your minus 96. A little capacitor here to help hold the voltage steady. Let's see. So yeah, that's pretty much it. So, yeah, I think I've covered everything on there. So that's it for the gates. So you have, these I was able to expand. I don't remember what the largest gate I had, like 12 inputs or something like that, or maybe even a little more on some of these gates. These seem to be pretty resilient, as to how many gates, diodes and stuff like that you can put on the inputs. If you didn't use diodes, you would have to use tubes for all these inputs, sort of like the modern MOSFET gates. They don't have diodes. They use a transistor for each input, right? I was wondering when I was putting this together, oh, can I get away with packing all these terms here, all the OR terms into the one tube? Will it be able to handle it and work? And it turns out it did. Another way to make a OR gate, this is just, something I didn't do, but something I might have had to do if this didn't work, is you can make OR gates, or NOR gates rather, right? NOR gates, by putting, here's one term of the AND gate, and then you could put another tube in parallel and make OR terms out of it, right? Here you put your 3 volts in on each one of these. But again, I didn't really need to do this. And then this would be just one of the AND terms and one of the AND terms here. But of course you end up using a lot more tubes, right? Because you don't have this would make an OR. So you just have the two diodes here. And what this eliminates in a way is then you don't have to have the diode here to perform the ORing function. You could just use these directly for your inputs, right? Because you don't need a diode there to separate the various OR terms. So this is that same gate we did on the other page, right, with 2 AND inputs and 1 OR input. And these are the 47K, still the same old 47K. Fortunately, I didn't have to resort to that, but that would have been an alternative that, maybe in a real world circuit that, the capacitances of the tubes or something like that made the gates didn't work, in real life. But fortunately, the resistance values I picked, seemed to work out pretty good, and I didn't need to resort to this. And it may be that if you build it faster with these more tubes, that maybe, if you build it with these more tubes, maybe it'll run faster. Another research topic maybe to try. I'm sure the old tube designers probably know the answer to that off the top of their heads. But anyway, that's an alternative. But it turned out that this circuit here worked good enough. This original circuit here works good enough for getting it to go. So I guess that's it for that video, and I'll talk to you later. Next time we'll do more of the traditional logic stuff, but this is the electronics part of it, with how to make a gate. Once you can make a gate, you can make the rest of it. To me anyway, is it's all downhill from there. So that's it for this one.